Okay, we're going to wrap up chapter 12 here by talking about section 6, the binomial theorem. Hopefully you're familiar with binomials, and there might even be a term or two here with which you are already familiar, and when we hit those, you may rejoice. Of course, you know a binomial is just an algebraic expression that has two terms, so it could be in the form a plus b. It's fairly easy to raise a plus b to any power, such as if we take a plus b to the first. Wow, that's really tough, Mr. Mark. A plus b, the quantity squared. You know not to distribute that exponent, right? Yes, we could use the FOIL method. That's absolutely right. A plus b to the third power. All right, well, that's just taking what you had for a plus b squared and multiplying, distributing another a plus b factor. And, you know, after 3 and 4 and 5, my goodness, things are getting rather tedious. But before you just dismiss all that, take a closer look. There are certain patterns that you need to see. For a to the fourth, sorry, a plus b to the fourth. The first term is a to the fourth. The last term is b to the fourth. Look at a plus b to the fifth. The first term is a to the fifth. The last term is b to the fifth. Now, if you just focus on the a variable in each one of those rows, what's happening to the exponents? For a plus b to the fourth, it's going from the fourth down to the third, down to the second, down to the first, and then I guess technically the last term there is a to the 0 power, because anything to the 0 power is 1. What's happening with each of those exponents on the variable b? And then you look at each individual term, doesn't matter which expansion here. What do you notice about the two exponents? All right, so we're raising it to whatever power. There are going to be n plus 1 number of terms. Okay, so we get to the first power, we had 2 terms. Squaring it, we had 3 terms. Okay, the first term is always going to be a to the n. The last term is always going to be b to the n. The exponents of a, yes, we saw that decrease by 1 from term to term, down to nothing, while the exponents of b increase from nothing. And looking at each individual term, the sum of the exponents of a and b is also equal to n. So again, we go back here. It's 5a to the fourth implied b to the first. 4 plus 1 is 5. 10a cubed b squared, 3 plus 2 is 5. Okay, so they're, again, just trying to highlight and emphasize this. Now, yes, there's simple patterns here for the exponents. The one decreases, the other one increases. The sum is always equal to n. What about those pesky little coefficients? You may have heard of Pascal's triangle. What we in the West refer to it, thanks to the explanation from a Frenchman by the name of Blaise Pascal. What a guy. If we write out just the coefficients in the expansion here, forget about the variables for a moment, it forms, if you write it in that shape, a lovely equilateral triangle where something really, really interesting happens. You can find all of the coefficients, the numbers in the next row of the triangle, by simply adding together the two numbers in the row above it, going obliquely left and right. They're the diagonals. So here's the expansion. We saw that a moment ago of a plus b to the fifth power. It had coefficients 1, 5, 10, 10, 5, 1. Yay, symmetry! The first term and the last term are going to have a coefficient of 1. So then 1 plus 5 gives you 6. 5 plus 10 gives you 15. 10 and 10 is 20. 10 and 5 is 15. Gee, this is sounding repetitious. 5 and 1 is 6. Yes, every single row here should have symmetry. So then Pascal's triangle can tell you what the coefficients are supposed to be. We know the pattern of the exponents. We could write out the expansion of anything. So let's try a plus b to the seventh using Pascal's triangle. Now it's one thing when you have Pascal's triangle handy. We know the first term is a to the seventh. We know the last term is b to the seventh. We know it should progress in the pattern from a to the seventh to a to the sixth, b to the first, a to the fifth, b to the second, a to the fourth, b to the third, a cubed, b to the fourth, a squared, b to the fifth, a to the first, b to the sixth, b to the seventh. And then all we need to do is insert those coefficients from Pascal's triangle. If we look at the seventh row, where's the seventh row? What, you didn't memorize it? 1, 7, 21, 35, and then you reverse that. 35, 21, 7, 1. Boom, there she is. Thus. It's a strange little animation to throw in there, but who am I? So if you have a copy of Pascal's triangle handy, sure, you can just read it off that as a reference. What if you don't have that? Okay. Back up a little bit here. Do you remember the function factorial? N factorial simply means we're going to take n times n minus 1 times n minus 2 times n minus 3 all the way down times 3 times 2 times 1. Oh, by definition, 0 factorial is 1, just so that we've got all our bases covered here, so to speak. To find a binomial coefficient, that is, a coefficient and an expansion of our binomial, we're going to take n choose r, which is defined as n factorial divided by the product of r factorial times n minus r factorial. See, the issue here is you need to make sure that you can find the right combination of values. So here's the long, tedious method of doing this. 9 choose 4. So again, in our numerator is going to be 9 factorial. In our denominator, 4 factorial times the quantity 9 minus 4 factorial, which of course is a little bit of arithmetic. 9 factorial divided by 4 factorial times 5 factorial. Now if we write all that out, okay, 9 factorial, 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Hey, wait a minute. Most of those factors will reduce down with every single factor in the larger of the two. Let's make this easy on ourselves. 5 factorial. So in our numerator, we're now just left with the 9 times 8 times 7 times 6, but we're left with all of 4 factorial, 4 times 3 times 2 times 1. Yeah, that shouldn't be too tough. And again, we can do some really, really easy reducing here. If we remember that, say, 2 and 3 give you a product of 6, and 4 is just 2 times 4 will give you 8. So yeah, that's not too tough. Now, please, if you're going to do it this way, do what I just showed you. Make sure that you're doing a little bit of mental math here and not just blindly typing all of those things onto your calculator. Oh, by the way, speaking of blindly typing things on your calculator, here's the key. Make sure you catch this. You're looking for the right combination of numbers. With your calculator, yeah, forget all that stuff. We need a combination. So push the menu button. I'm sorry, we're looking for under option 5, our probability menu. We're looking for, what's the key phrase I just tried to throw at you? We're looking for the right combination of numbers. So that's option number 3, combinations. That takes you right back to your calculation screen. Okay. Now it's waiting here with some calculators here. The way that's written out, instead of the nice fraction that we just saw, 9/4, the wonderful people at Texas Instruments have tried to turn it into horizontal there. So we're going to type in 9. And now we need to put a comma, which of course is over here, bottom left corner. So this is going to tell us all the combinations of 9, choose 4. Wow, that was a lot less writing, wasn't it? Now, don't mess this up. Don't get confused because permutations and combinations are awfully similar. We're not looking for the permutation of the right values. We're looking for the right combination of numbers. So yes, I'm going to keep saying that about 57 more times. So the combination of 100, choose 3. Yeah, I mean, you could, the 99 divides by 3. The 100 divides by 2. Yeah, but the calculator does it. Oh, here, I'm sorry. I forgot to point out. This is really, really interesting. So the combinations of 100, choose 3 is 100 factorial over 3 factorial times g. 100 minus 3 is 97 factorial. And that'll give us 161, 700. What about the combinations of 100, choose 97? What's 100 factorial over 97 factorial times, oh gee, 100 minus, hey, wait a minute, that's 3 factorial. So the combinations of 100, choose 97 or 100, choose 3 turn out to be the exact same value. Okay, and that's what they're showing you here in the lovely blue box. So again, 5, choose all of them. Look at the one at the end there. 5, choose 5. There's only one way that you can do that. 5, don't choose any of them. Choose 0. There's only one way that that can happen. Out of 5 things, choose one of them. Well, there's 5 different outcomes. And those combinations there coincide exactly with the 5th row of Pascal's triangle. So yeah, we could write that as our lovely combinations with the funky little, again, those aren't fractions inside the parentheses. Notice there are no fraction bars. There are no nice little horizontal segments telling you to divide. Wrong notation. Okay, blah, which leads us then to the binomial theorem, which is just writing everything that we've discussed about the binomial theorem in our fancy schmancy notational form here. So the coefficient on the first one, n choose 0, that's always going to be 1 times a to the n power. And then we're going to take n choose 1 as the coefficient, and then take A and knock that down by 1 degree, and B shows up for the first time to the first power. All the way on down there, so the next to last one is going to be n choose n minus 1, and then the last coefficient, n choose n, that's going to be a 1. So we're going to write this out. Yes, we already saw the answer to this. We know all the answers to these. What I'm expecting to see with your work on OneNote is writing out the expansion here, following the directions. In this case, we're going to take x plus y to the fourth power by writing it out using the binomial theorem. Okay? So the first one is 4 choose 0, 4 choose 1, 4 choose 2, 4 choose 3, 4 choose 4. And then our x's go from x to the fourth, third, second, first, and 0. It disappeared. And the y's are going to be increasing. There is no y term, y variable with the first term. Y to the first, second, third, and ending with the fourth. So now it's just a matter of calculating those right combinations. So 4 choose 0, that's 1. 4 choose 1 is 4. 4 choose 2 is 6. 4 choose 3 is 4. Combination of 4 choose all of them is 1. So we then write those out as the coefficients. It's 1x to the fourth plus 4x cubed y plus 6x squared y squared plus 4x y to the third plus 1 y to the fourth. And again, the coefficient of 1s, you don't need to write those out. Suppose, for a very, very specific reason, we need to know the value of one individual, one single term in a binomial expansion. Well, again, with the help of combinations, we can figure out what that coefficient is, and we know the pattern of the exponents. Okay? So if we were to take, oh my goodness, they turned that binomial into something just a little bit more interesting, 2x plus y to the 20th power, and we're asked to find the term that contains x to the fifth. All right, so that means r is 5, n is 20. Be careful, in this case, a is equal to 2x. So it's that 2x that we're going to have to raise to the fifth power. And again, the sum of our exponents has to equal 20 because, again, that was given to us there. So if that's going to be x to the fifth, that means 20 minus 5. That has to be y to the 15th. And then we're looking for the combinations out of 20, choose 15. Now notice here, taking 2x raised to the fifth power not only gives us x to the fifth, but you also have to take 2 to the fifth power, which is 32. And again, with our calculators there, the combination of 20, choose 15, multiply that by the 32 to get our final coefficient of 496,128, x to the fifth, y to the 15th. And yeah, the proof of it, you really don't need to worry about that. All right, so again, take a look at the assignment listed down at the bottom of all of this on that other page from OneNote, and we'll talk again soon.